Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're going to talk about antimatter rockets. So let's dive right into it. So what is antimatter itself? Basically, first the idea, the mathematics of it was done by Paul Dirac in 1928. Yes, this is an ancient mathematical concept, and the physical reality, basically experimental proof, was discovered in 2 August 1932. Yes, this is ancient technology basically. So you have to understand, now this is the line that you will see. Now you are like, okay, what does that line mean, antiproton? Basically the magnetic field was going this way, and by every stretch of the imagination it's supposed to be this way, but it happened this way because it's anti, the magnetic poles are inverted. So whenever you talk about antimatter, the most common thing people say it's invert of matter. Now that's true and false in other ways. Basically, if you want to be precise, you have to say it also not only it is like opposite in terms of electrical charge, but it also has negative magnetic momentum. That is why, like, you cannot just say, oh, in antimatter the electron is proton. You can't say that because it has inverted. It's not just like it's like a mirror, how you write something and it becomes inverted. It's like that. It's not like, okay, instead of electron there is proton, instead of proton there is electron. It's not flip of that, it's inverted of that, or not only in electrical charge but also in magnetism also. Now that may not be a big deal to you and I, but on a quantum level that is a very defining factor. So the first thing that we discovered was basically anti-electron. That's how we know the pathway, and we named it basically positron. After positron, we started to try to build higher and higher capacity colliders, and we reached to anti-proton. Basically, proton is much heavier than electron. Then very recently, basically in the last few years, we reached anti-hydrogen, basically where we finally built a molecule of antimatter, not just like subatomic particle, a proper molecule. So this is antimatter, absolutely scientific fact. So what is the science behind it? Why so many people are attached to antimatter? Basically, it is antimatter plus matter equals 100% equal to mc square. So whenever you are doing fusion, you must be aware of that fact that some amount of matter gets converted into energy, but it's always some amount, and it's barely 1%. It's like, it's always very little. It's like 0.01%. It's very little. When you're talking about antimatter, it's 100%. It's like you have 1 kilo of matter, you get 2 kilo of basically energy output. So that is the most amazing part. Basically, it's 100% efficient in terms of E equal to mc square. So what happens when you have anti-electron meeting with electron? Basically both will collide and it will create 2 photons of high energy gamma radiation. Now is that all? Does all you get is a gamma energy? Well, yes and no. Basically, if you are doing with light low energy, quote unquote, you will get that. But what if you wanted to start colliding hydrogen and anti-hydrogen? Then you will get different outputs. Then you will gamma rays, electrons, positrons, and neutrinos that you must be familiar with, like our sun keeps bombarding our upper atmosphere. So this is how you can create neutrinos in Earth's atmosphere. Basically, if you combine something big, let's say a chunk of matter to another chunk of antimatter, not anti-electrons, antimatter, then you will get these things also. At that point, do not just think, okay, everything gets converted to gamma rays. Most of the things will be converted into whether electrons, positron, and neutrinos. So that's the science of it. So let's do a reality check. Now the first thing that makes me mad is that almost all science fiction generally treats it as an energy source. It's not an energy source. It's not found naturally anywhere, because if it is, it would be so diluted that it hasn't interacted with any matter, and if it does, boom, and it will create neutron. So that's how we are getting neutron bombardment. So it's not energy source. You can't just go somewhere and mine antimatter. So it is an energy carrier. Basically, let's say you want to create a battery that is like god level awesome. This is the best option you have. It is an energy carrier. Basically, you have 1 gigawatt of energy in one place. You want to travel, carry it to some place. Antimatter is your best option. Now, because I specified that you cannot just go and mine, you cannot drill into earth to get antimatter or put up space funnels and all that, because even if you did that, you will barely get few atoms. So you have to make it before you use it. Now how do you make it? Basically, E equal to mc square, you run that in reverse. Basically, you put in the energy. So to get 1 megawatt equivalent of antimatter, you have to put in 1 megawatt. Now that sounds okay. It's like, we have a power plant that produces hundreds of megawatts, so that should not be an issue, until you realize is the efficiency aspect. Basically, it's ludicrously inefficient. To give you a context, right now you have to put basically hundreds of gigawatt to get 1 megawatt out, if you're lucky. And even the engineers that are like, hey, we can make a better one, cheaper one and all that, they are still expecting 1% efficiency in 1000. So it would be like, okay, 1000 megawatt in terms of electrical energy, 1 megawatt out if you are lucky. So flat out, E equal to mc square plus the inefficiency makes it practically a energy sink. Now you can do that in basically, let's say, in a space where you are just harnessing insane amount of solar energy. You can do that. Sun has more than enough energy, but on Earth you simply can't do that. So in terms of cost, how much it's gonna cost is basically expensive beyond belief. There is no numerical system that can even count that high. $1 trillion and all that, yeah, it's beyond belief. And where do we make that? We basically make them in colliders. You can, like the scientists who are proposing they can reduce the inefficiency aspect from million to 1 to 1000 to 1. They are suggesting that these colliders, while they are, engineering masterpiece, they are built for precision. They are not built for engineering output. So they can make this puppy from costing $2-3 billion to few $1 million. So that's the reality check. Even if they did that, even if they magically managed to reduce the inefficiency, you are still talking about putting like at least 1000 times more energy to get something out of it. So that's the reality aspect of it. It's not an energy source, it's an energy carrier. And on top of that, I have been making videos directly about using nuclear option as a space propulsion. So you had a nuclear fission. Side effect of that, the radioisotropic byproducts. Basically, if you landed on a comet, that comet is irradiated. What about if you use fusion? Fusion does not have the side effect of having radioactive byproducts. However, it still has the same problem as nuclear fusion, where it has high energy neutrons. Basically, it will make everything radioactive. Less of an issue compared to basically fission, but it still makes everything radioactive. On top of that, you have the luxury of going to a-neutronic bit. Rather than having neutron output, you can have proton output. If you have proton output, you can control it, channel it, and you can have very high conversion efficiency. I'm talking as high as 60 to 90% conversion efficiency. That is mind-bogglingly awesome if that can be done. And that is the magic that everybody wants to achieve, the a-neutronic fusion of helium-3. So in terms of space energy, if you really want to do something awesome, you will take proton and boron and boom. That way you will have very minimal neutron flux, less neutron flux than what you will get using helium-3. And not to mention, helium-3 is rare as hell. Like you cannot, like everybody's like moon has helium-3. Yeah, it has helium-3. Like there is less helium-3 there than you have gold in seawater. Basically, take seawater, just randomly, just filter it out. You will find more gold there than you will find helium-3 on lunar regular. Helium-3 is not something that you can just have. Oh yeah, just mine it and you will have gigatons of it. It's not something like that. So okay, there you have the luxury of going a-neutronic, but here it creates a very hard ionizing radiation. So it does not create neutrinos, but it creates ludicrously high energy gamma particles. Basically, it's a very difficult thing to manage for health aspect of point. On top of that, it makes everything radioactive. It's like your reactor you started, like a first few hours of operation, it will directly turn containment vessel inside into radioactive, then the outer body, then the whole ship will turn into radioactive. It will be basically like Chernobyl 2.0. The radiation is very serious when you're talking about antimatter. Unless you have like magic technology that magically blocks radiation, this is flat out unfeasible. So on top of that, let's say you have some magical system that allows you to stop radiation or harness it, which would be awesome if you can figure out how to harness gamma radiation. Let's say you figure that out. After that, you still have the issue of impossible to store. It is not something that we can store. You must understand that we have been making antimatters for almost 50 years. So we learned it the hard way that you have to keep it at absolute zero, and I'm talking serious absolute zero. I'm not talking like okay, 1 Kelvin or 2 Kelvin. Like it has to be like 0.0000001 picokelvin or something like that. Like it has to be as close to absolute zero as we can get. On top of that, to make sure that it does not touch anything, we have to use what we call pinning trap. Basically, it's a magnetic trap, something like this. Basically, you have magnetic field that is trapping it. If this fails, it will touch the matter and you have a nuclear bomb. On top of that, it's very short-lived. So I told you, like we have been building antimatter like for a very long time. We built it. Right now the record is like 17 minutes. That's how long the antimatter lasted. On top of that, it's very low density. Basically, even if let's say you are like, hey, to go to Alpha Centauri, we barely need to make, let's say 1 ton, and 1 ton is too much. Let's say you only need 1 kilogram. I'm talking everything like the radiation shielding and all that. Like you are like, okay, 1 ton. Awesome. Here's the deal. The 1 ton would not be this big or this big. It will be huge, because you cannot put two antimatter very close to each other. You have to dilute them with something. So by default, it's very low density. And not to mention, it is not safe to store. Basically, you cannot be like, okay, these are the traps that we actually use. Like this is something we built in real life. It's not something that you can, again, in here, there is only 1 or 2 electrons. So even if it detonates, it won't cause too much damage. But You have to understand, this is not something that you can like, oops, because you can design a fission reactor that's like, oops, it's oops proof. Basically, there are designs that we can build like, okay, if somebody makes a mistake, it's shut down. Again, you will still have radioactive waste, but it can shut down. In terms of fusion, we cannot do oops. Even if you want to, you cannot do oops, because if you put too much fuel, the plasma will expand. The moment plasma will expand, the temperature will drop. The moment the temperature drops, fusion stops. So you cannot detonate it. I have no idea how the heck the Expanse TV show just shows nuclear reactor going into critical. Unless, like, again, I can justify that, okay, it's a military system, that they have a system to detonate it, but practical sense, you cannot detonate a fusion reactor. Here, it's completely opposite. It's like you make one mistake, like one coil malfunction, kaboom. The temperature rise, it starts to vibrate, kaboom. Everything will lead into kaboom. And the higher the concentration you have, basically, like, let's say 1 gram, or because here we have like not even measurable, it's like countable, yeah, 18 atoms, 20 atoms, or something like that. If you have like a gram of it, yeah, good luck with that. So after that, the moment you type antimatter and all that, the first thing people will say, it's an order of magnitude more powerful than chemical. That's 100% true, absolutely mathematically, absolutely correct. However, the thing that the people generally ignore, it's only a cube then basically fusion. So if you have a good fusion system, specifically a neutronic one, you're not getting too much more. Basically, in terms of usable output, fusion would be like you have to carry twice as much. Now here's the thing, antimatter is unstable as hell. So I already told you, like, we put the best engineering out there, we put the best science out there, we can only make it stable for 17 years. Here's the thing, what is the life of basically hydrogen? How long you can keep liquid hydrogen? Basically, you have a ship, let's say, you can utilize hydrogen for many reasons. Basically, you can have like hydrogen packed as a liquid state outside of your ship. Why? It acts as a very good radiation shield. Basically, if you are going through even a very charged environment, plasma storm and all that, you'll still have a very good radiation shielding. And even if something happens, let's say it get punctures and all that, there is vacuum outside, so it will not catch on fire, so you don't have to worry about it. You ignore it, it will freeze up. You don't have to worry about it. Here in antimatter is completely opposite of that. Antimatter is something that you have to protect. So it's only good for, antimatter is only good for science fiction. And I don't blame John Roddenberry when he came up with like Star Trek and antimatter. At that time, people did not knew as much about it. So yeah, it looks cool. But again, there was one YouTuber who makes a video about Star Trek. He keeps saying, like, in Star Trek, every Tuesday, a reactor keeps blowing up. So yeah, that happens. That will happen. If you are using antimatter, it is that unstable. Why would you use antimatter if it's not that powerful? And on top of that, all the equation, all the mathematics is like, they don't even worry about how the heck you are containing it. It's like, how the heck you are making sure that under no circumstances, no matter what happens, magnetic system does not fail. Under no circumstances, the cryogenics does not fail. How do you make sure that? Like, it cannot be made sure. Like, you cannot build a system that is like, impervious to everything. In hydrogen, you can have a system like, for if you have hydrogen, the biggest issue you will have is like, hey, to make sure the reactor does not shut down. That is why making a fusion reactor is so difficult. Igniting is the difficult part, not shutting it down. And not to mention, it has another multiple error. And if you are traveling to, let's say you are making a ship, you're going to Alpha Centauri, you will find hydrogen. Hydrogen is the most abundant thing out there. So why would you not use hydrogen that you can easily go anywhere, refuel it, use it as a radiation shield? So why would you use the antimatter instead of hydrogen? That is the whole aspect. Like, it's very good for science fiction. Star Trek is the main reason for that. But other than that, once I started to research it more and more fine detail, it's like, yeah, why would I want antimatter anywhere near my ship where it's like, oops, kaboom, oops, boom. It's like, why would you want to do that? So it's not that powerful. Like, once you actually do the numbers and you can read the articles of Wikipedia and all that, it's not that powerful. Like, fusion is much better. So this was my presentation about antimatter propulsion system. I hope you liked it, learned from it. In that case, please click the like button. If you didn't like it, didn't enjoy it, I would urge you to press dislike, press it twice to show me your extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.